Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss one-dimensional wave equation and its solution to the stressed vibration string. Let's begin. Let us consider the motion of a stretched string . The stretched string fixed at its ends let small l be the length of the string . Having fixed ends O and R, we consider O as the origin of OR as x-axis and OY is perpendicular to that of x-axis, for which the motion of the string is in xy plane. These are the assumptions we have to consider to that of treatment of the motion of that of string. What are these assumptions? The string is homogeneously perfectly elastic. The tension is very large as compared to that of weight of the string, so that gravity has no effect on that of string. Third assumption, the motion of the string is transverse vibration in a vertical plane. These are the assumptions are made in that of treatment of that motion of the string. Now let us consider, let the string be released from rest and allowed to vibrate transversely. Let us consider a small portion PQ of that of string, so that the tension is tangential to the curve of that of string at point P and Q. The tension is tangential at point P and Q. Here is tension T1, there will be the tension T2. Hence, let T1 and T2 be the tensions at point P and Q. The horizontal components of that of tensions, let draw like this. This be the horizontal component . This angle let take theta 1, that angle let theta 2. The horizontal component of T1, this one the horizontal component, that one is the vertical component. The horizontal component of that of T1, that one is T1 cos theta 1, T1 cos theta 1, and its horizontal component, that one is T2 cos theta 2, while the vertical components, its vertical components, that is T1 sin theta 1, that is T1 sin theta 1, that vertical component, that is T2 sin theta 2. But there is no motion in the horizontal direction, then the horizontal components of that of tension must be equal, since there will be no motion in that of horizontal direction. That's why we can say mathematically that T1 cos theta 1 is same T1 cos theta 1 is same as that of T2 cos theta 2. Let I prefer it as T. Why these two are equal? As there is no motion in that of horizontal direction, then the horizontal components of that of tension must be equal. We equate, that is T1 cos theta 1 is equal to T2 cos theta 2, and that value is same as that of T. As y is the vertical displacement, let I prefer y, say it as the vertical displacement. The upward acceleration that is del 2y del 2 the rate of change of displacement. This one is the upward acceleration, and if I prefer small m is the mass per unit length, mass per unit length of that of string, and del x the length of small portion of that string, length of small portion of that string. Y the vertical displacement, del 2y del T2 that is upward acceleration, small m mass per unit length, del x the length of small portion of that of string. This is x, that point is x plus del x, and that displacement section is del x. Therefore, by using Newton's second law of motion, according to Newton's second law of motion, the net force is equal to mass into acceleration. Hence, in that of case, the net force acting in that of upward direction. Therefore, we can say that net force will be T2 sin theta 2 minus T1 sin theta 1. This is the horizontal component. T1 sin theta 1, T2 sin theta 2. Since that net force acting in that of upward direction, we can treat the net force will be the horizontal components of that of tension, is equal to mass, that is m del x. Small m is the mass per unit length, del x is the length, therefore the mass of that string of that of small portion. Then the acceleration, the upward acceleration, that is del 2y del T2. Let equation number, here let prefer it as equation number 1, that one be equation number 2. Now, using equation 1 and 2, using equation 1 and 2, we get, that is T2 sin theta 2 t2 sin theta 2 minus t1 sin theta 1, let divided by t. Here m del x del 2y del 2 divided by t. Now we can separate t2 sin theta 2 by t minus t1 sin theta 1 by t is equal to m del x divided by t del 2y del t2, or since t these two are equal, therefore I can supplement here t2 sin theta 2, that means in place of t I can substitute t2 cos theta 2, therefore t2 sin theta 2 divided by t2 cos theta 2 minus t1 sin theta 1. Again in place I also can substitute t1 cos theta 1, t1 cos theta 1 is equal to m del x by t del 2y del t2, or that is t2 cancel out, sin theta 2 cos theta 2, that is tan theta 2 minus t1 cancel out, sin theta 1 by cos theta 1, that is tan of theta 1 is equal to m del x by t del 2y by del t2, that is equation number 3. But what is theta 1 and what is theta 2? Tan theta 1 and tan theta 2. But we know that the slope of that of curve, the slope of that of curve of that of string at x and x plus del x are nothing. The slopes are right here. The slopes are b tan theta 1, that is del y del x at that a point x, and tan theta 2 at del y del x point x plus del x. Hence equation 3 will be, therefore equation 3 becomes tan theta 2 minus tan theta 1 del y del x x plus delta x minus del y del x at x is equal to m del x by t del 2y del t2, which implies dividing del x on both sides, it is del y del x x plus delta x minus del y del x at x divided by del x is equal to m by t del 2y del t2. Let that one be the equation number 4. So when del x tends to 0, as that q point tends to p. Therefore, equation 4 becomes, when that p point it tends to q point, or that means del x tends to 0, that point is same to that particular point. That equation will be changed to the second order differentiation of that of del 2y del x2, that sequence, that will be, that is m by t del 2y del t2, or del 2y del x2 is equal to, del 2y by del t2, just change it. Therefore, that is t by m del 2y by del x2. Equation number 5. Now putting c square is equal to t by m, equation 5 becomes, equation 5 becomes, that is del 2y del t2 is equal to c square del 2y del x2, equation number 7. That one be the required expression. This equation is known as, we can say it as one dimensional wave equation, one dimensional wave equation, which governs the transverse vibration of that of string, that is the one dimensional wave equation. Now our task is to find out what should be the solution of that of wave equation. The solution of the wave equation, the solution of that of wave equation. This one be the one dimensional wave equation in the string under transverse vibration. Let me prefer one dimensional wave equation in the string under transverse vibration, is given by, that is del 2y del t2 is equal to c square del 2y del x2, that is equation number 1. And the string of length is L. The string of length be L and is fixed at one end, fixed at both the ends. Then the boundary conditions are, the boundary conditions are y 0t is equal to 0, y lt is equal to 0, and y at xt is equal to f of x. These are the boundary conditions. As the string is at rest, as the string is fixed, that means it will be at rest. As the string is fixed at both ends, then the displacement is 0, y is equal to 0, the displacement is 0. Therefore, we can write here del y by del t at t is equal to 0 given the initial velocity, that is del y by del t at t is equal to 0. Let I prefer it as g of x, that equation number 5. Using that method, using the method of separation of variables, using the method of separation of variables, let the solution be of the form y is equal to x, a function of x only, t is a function of t only. Therefore, del 2y del t2 will be x, del 2t del t2, and del 2y del x2 equal to t del 2x del x2. Putting these values in that of equation 1, then equation 1 becomes, we use the separation variable method to solve that differential equation, x del 2t del t2 is equal to c square t del 2x del x2, which implies that divide xt on both sides, that is x del 2t del t2 divided by xt is equal to c square t del square x del x2 divided by xt, which implies 1 by t del 2t del t2 is equal to c square by x del 2x by del x2. Since this one is the function of t only, that one is the function of x only, therefore we can equate to a same constant, that equations let, which implies 1 by x del 2x del x2 is equal to 1 by c square t del 2t del t2 is equal to minus lambda square. Let then one by x del 2x del x2 is equal to minus lambda square, which implies that is del 2x del x2 is equal to minus lambda square x, which implies del 2x del x2 plus lambda square x is equal to 0, that is we can say that is d square plus lambda square x is equal to 0. D means that is the differentiation, the second order differentiation. Therefore the auxiliary equation is given by the auxiliary equation is given by m square plus lambda square is equal to 0, which implies m is equal to plus minus lambda I. Then the solution is written like this: x is equal to a cos lambda x plus b sin lambda x. That equation number, let I prefer it as equation number lambda square be 7, that one be 8, that one let equation number 9. Again this one equal to that constant. Again let I take again 1 by c square t del 2t del t2 is equal to minus lambda square, which implies del 2t del t2 is equal to minus lambda square c square t, which implies del 2 del t2 plus lambda square c square t is equal to 0, which implies d square plus lambda square c square t is equal to 0. Now the auxiliary equation, is given by that is m square plus lambda square c square is equal to 0, which implies m square is equal to minus lambda square c square, which implies m is equal to plus minus lambda c phi. Then the solution, that is t is equal to, that one be the equation, then its solution t is equal to c cos lambda ct plus d sin lambda ct. These are the solution at equation number 10. Now we use the boundary conditions. These are the boundary conditions. First implement 1, 2, 3 boundary conditions are to be substituted in these two solutions. One is the solution of x, another one is the solution of t. That's why we can write now y 0 t is equal to x 0 t as a function of t is equal to 0. Also y l t, that is x l t as a function of t equal to 0, which implies t at t is not equal to 0, therefore that term is equal to 0. Then x at 0 is equal to 0 and x at L is equal to 0. X at 0 is equal to 0 and x at L is equal to 0. From that of equation number 9, the solution of x, I can write here from equation 9, we get a is equal to 0. From equation 9, putting its values here, we get a is equal to 0 and b lambda l is equal to 0. Okay, let us a is equal to 0 and b sin lambda l is equal to 0, which implies sin lambda l is equal to 0 as b is not equal to 0, which implies lambda l is equal to n pi, where n is equal to 1, 2, 3 ... Therefore lambda will be n pi divided by L. Let equation number 12. So the value of x will be how much? Therefore the value of x as a function of x only is equal to b sin pi n pi x by L. Just noted it. Equation number 13. Again the value of t, then the value of t, the function of t only, will be c cos n pi ct by L plus d sin n pi ct by L. Equation number 14. Just noted. Now therefore the solution of that of differential equation, the solution of that differential equation is given by y as a function of y xt, that is x as a function of x only, we separate t as a function of t only, which implies y xt, the general solution, will be sin n pi x by L. In that two conditions, n pi x L as common from these two, we get c cos, for that of nth term, let I prefer it as yn, cn cos n pi ct by L plus dn sin n pi ct by L. This one is here another constant will be there Bn, but Bn constant has been included in Cn and Dn, has been included in Cn and Dn. That's the reason I don't mention here the constant Bn. Okay. Let equation number 15. Hence, by the principle of superposition, the general solution of equation 1, hence by the principle of superposition, the general solution equation 1 is given by, that is general solution y of xt will be summation of these terms, summation over y n of xt from that of n is equal to 1 to infinity. That means summation over n is equal to 1 to infinity Cn cos n pi ct by L plus Dn sin n pi ct by L into sin n pi x by L. This is the general solution of that of first equation. This one is equation number 16. Here Cn, Dn are to be found out from that of boundary conditions, and the function y n xt, y n of xt are called the Eigen functions. These functions are called the Eigen functions, or we can say it as the characteristic functions. The values of n pi x by L are called the Eigen values. N pi x by L is known as the Eigen values of that of what? Eigen values of that of vibrating string. Eigen values of vibrating string. This one is the general solution of that of wave equation. So, the entire video lecture is based upon one-dimensional wave equation and its solution of that of one-dimensional wave equation for that of case vibration of that of string in a transverse way. Take a overall look here. This is the one-dimensional wave equation. We take the assumptions and proceed mathematically. Then the solution of that of wave equation and its boundary conditions. We get that of solution by using variable separation method. X, and then we get for that of t, and putting that of boundary conditions, finally we get yn of xt and the general solution of that of given equation 1, finally get that one. This one is the final solution, or we can say the general solution of that of vibrating string. This is a overall video lecture that is based upon the wave equation and its solution for vibrational modes of a stressed string. So, with this useful and informative notes, let me wind up this session. Thank you.